Okay. Hi, my name is Ed Levin. I'm director of the Duke Center on Addiction and Behavior Change. I welcome you to the seminar series. This is together with the Center on the Study of Adolescent Risk and Resilience, and really value their collaboration. We're going to have today's speaker, and I'll introduce him in just a minute. And also, we'll have a second one we're going to collaborate on this semester on December 1st. And that'll be Elizabeth Lippert from the University. I just wanted to say that we're going to be starting again. We'll have a combination of live and online talks. We're going to start on January 12th with Christina Mead, and then continue on with a variety of speakers approximately twice a month that we'll be having some here in the Dipp's Cube and some online, and then the ones here will be hybrid. So today I'd like to introduce actually an old colleague who used to be here at Duke, Dr. Merideth Addicott, who is associate professor at the Department of Physiology and Pharmacology at Wake Forest School of Medicine. And Dr. Addicott earned her PhD in 2009 in neuroscience from Wake Forest University, and came here as a postdoc and then assistant professor through 2017 here at Duke, and then 2017 through 21 at the University of Arkansas, and then more recently came back to North Carolina. Wonderful move, have her fairly local, and then today she's going to speak to us about her work in the effects of smoking and smoking cessation on stress, cognition, and DNA methylation.
Thanks. Can everyone hear me okay? No? Is that better? Okay. A bit closer. I'm a very quiet talker. Okay, so today I'm going to talk about the results of a study I completed recently. So in this study, I decided to study ex-smokers. And so why should we study ex-smokers? Well, most people in the US who have ever smoked are now ex-smokers. Do I need to use that? I'm too quiet. So why should we study ex-smokers? The majority of people in the US who've ever smoked are ex-smokers, but smoking cessation is really hard, and the majority of people who try to quit relapse. So can you see it's nowhere near where it is on screen. Okay, so as you can see from this relapse curve, the first 7 days of a quit attempt are pretty much a cliff. Most people go back to smoking. And after about 6 months, you got about 10% to remain abstinent. So while the majority of smokers say they want to quit, and about half of them make it past their quit attempt, only about 7% are ultimately successful in maintaining abstinence. And the majority of research on smoking has used non-smokers as a comparator group. But part of the problem with that is that there's more than 8,000 chemical components in cigarette smoke that smokers are exposed to that non-smokers are not exposed to. And they might also have pre-existing differences in genetics or personality traits that predispose some people to developing tobacco use disorder while others don't. There's a lot of differences between these two groups above and beyond just the differences in tobacco use disorder. So why not study successful ex-smokers instead? Differences between smokers and ex-smokers might be pre-existing or the result of cessation, but they're definitely not due to the toxin exposure or to the risk of tobacco use disorder. And comparing individuals who quit smoking to those who continue to smoke can also provide valuable information regarding the progression of smoking-related effects or the recovery from those effects. And we probably can't help smokers think and act like non-smokers, but potentially we could help smokers think and act like ex-smokers, and maybe that would help their next quit attempt be more successful. Okay, so this was a small R21 with a really simple design. We just brought everybody in, and they were consented and screened for eligibility, and then they came back on one study day in which they underwent MRI and completed measures of distress tolerance, which I'll explain in a minute. I ended up with 31 smokers and 31 ex-smokers. They were aged 25 to 55. They had a similar number of years of education, and their nicotine dependence was similar between smokers' current nicotine dependence and ex-smokers' past nicotine dependence. Surprisingly, their pack years were similar too. Pack years is the number of packs of cigarettes per day times the number of years of smoking. So it's a measure of cumulative dose of cigarette smoke they've received. And so while ex-smokers may have had fewer years of smoking because they quit a while ago, they were actually smoking more cigarettes back in the day. Smokers today just smoke fewer cigarettes, maybe because of all the regulatory restrictions or because cigarettes are more expensive. Where these two groups differed was in the duration of the last quit attempt. I included the values among the smokers who had ever made a quit attempt just to have more spread in the data. But on average, they relapsed within 3 months, whereas the ex-smokers had been quit an average of 9 years. Okay, so I collected a whole bunch of different data, so I'm going to break it down and first talk about stress and negative affect. So we've known about this stress-smoking relationship for a long time. This ad is from 1935. It's a guy sitting in a dentist waiting room being handed a cigarette. And it says, "To anxiety, I bring relief. I'm your best friend. Try me, I'll never let you down." And we know that people with tobacco use disorders tobacco use disorder disproportionately affects people with mood disorders. Smokers are more likely to have depression, anxiety, and psychological distress. And we also know from both human subjects research as well as animal models of substance use disorders that stress, like emotional or physical stress, can trigger cravings and drug-seeking behaviors and can also increase the risk of relapse. But it's still uncertain if mood disorders are a cause or consequence of smoking, might develop together for several reasons. For instance, smokers may use cigarettes to alleviate stress and therefore just lose other coping skills. There's also some neurobiological explanations, like nicotine has antidepressant effects, and maybe chronic smoking tolerance develops to these effects, and therefore withdrawal from smoking could worsen depressed mood. There's also been preclinical research suggesting that the acetylcholine system modulates the behavioral response to stress. Of course, nicotine binds to the nicotinic acetylcholine receptors. So possibly smokers report being more stressed than non-smokers because the nicotine itself has sensitized them to stress. So how do we measure this stress in the lab? Well, I use the paced auditory serial addition test. This is a mental math test that was originally developed way before computers, where experimenters would just say the number out loud. Participants or patients would just answer with the sum. It was originally developed to test like traumatic brain injuries or multiple sclerosis to see those effects on cognitive performance. And what happens in my version is everyone starts out by seeing a 0 on the screen, and then they're told they have to add the number they see with the next number. So that 0 turns to a 3, and they use a response number pad in a scanner to indicate which of those 4 numbers below is the correct sum. So 0 plus 3 is 3, 3 plus 5 is 8, 5 plus 1 is 6. And it goes pretty fast. They only have 1.5 seconds to respond. The problem with this task is that it's known to create a lot of anxiety and frustration, which affects performance and participant retention. So people doing research on traumatic brain injuries and multiple sclerosis are actually discouraged from using this task. But the researchers who are interested in eliciting stress decided to double down on this and make it more frustrating by adding a negative auditory feedback whenever they are incorrect or late. So what happens in my version of the task is it starts out, there's an easy phase where they're shown these numbers one at a time, and they really only have 2 options to choose from. The sum is never 0. Every time they're correct and on time, they hear a nice tone, bing. And that gets interspersed with resting state. And then in the distress phase, we make it a little bit more challenging. Now there's 4 numbers to choose from. Oh, and I should have said back here, when they're incorrect or late, they don't hear anything. So they hear the bing when they're correct and nothing when they're wrong. Over here now, when they're correct and on time, they don't hear anything. When they're incorrect or late, they hear a buzzer that goes, eh. And to make things a little bit more interesting, we tell them that there's now a computer algorithm that decides a new cutoff on each trial. So on some trials, they may have made the response correctly and within that 1.5 second response period, but they're still going to hear the buzzer because on that trial, they only had like 1 second to respond. In actuality, I've inserted some forced fail trials. So no matter how well they're doing on the task, everyone's going to hear the buzzer the same number of times. And then just because I don't want to pay for the extra time in the scanner when I'm not scanning them, I have them come out of the scanner and sit down at a desktop computer. And now they can continue to play that task for as long as they want. We don't tell them the maximum duration of 20 minutes. But now every correct answer, they earn a point that can go towards a performance bonus. So just a small financial incentive to keep going. But they can quit at any time. So how long they continue doing this task is a measure of their distress tolerance. And distress tolerance is the ability to pursue a goal, like earning that bonus money in spite of negative emotional stress. And that parallel with substance use disorder and tobacco use disorder is that we think, when you have cravings for the drug, you have to have a lot of distress tolerance to not use the drug and or to maintain abstinence during a quit attempt. And the literature has shown that distress tolerance tasks like this are associated with the ability to quit and stay quit, not only for tobacco, but other substances. But just to go back, so of course we give them this mood rating scale in between these tasks. These are the results of that mood rating scale. This is the average of the negative mood scores for anxious, frustrated, and irritated. Higher scores are more negative mood. As you can see, the smokers here in blue had a pretty steep increase across those 3 time points. But the ex-smokers weren't quite as stressed out. And there was a significant difference between these 2 groups. In spite of this, I didn't see any differences in those distress tolerance measures, though. It didn't affect how long they were able to keep going. I'd shown that previously, but in this sample, it seemed like everyone just played to the bitter end, regardless of how angry they were. So I will come back to this negative mood in a few minutes, but next I'm going to move on to the cognitive performance of the PACE-AT. One of my eligibility criteria was that they had to be able to perform this task at 70% accuracy during the screening day. There were some people that just cannot stop hunting and pecking, and they're just going to do the task, so I eliminated them. But there was still a difference in performance between the smokers and ex-smokers. The smokers performed a little bit worse, which is pretty consistent with the literature suggesting that smokers have some deficits in like attentional control, response time, and so forth. So this top line is the number of trials, or the percentage of trials in which they heard that ping when they were correct and on time. And then across the 3 conditions, the smokers were performing a little bit worse, and everyone's performance got worse during the distress conditions. And then remember, I had those forced fail trials. So when you include every single buzzer sound as being incorrect, you look at just the number of trials in which they heard nothing, they were correct and on time. That did not differ. So in other words, they were hearing the buzzer the same number of times across the 2 groups. Even though the smokers were getting more incorrect, they were getting them incorrect on trials, they were going to hear the buzzer anyway. So even though the smokers were reporting more negative affect, it wasn't just because they were hearing the buzzer more often. And lastly, there's no differences in missed responses. The smokers also had slightly slower reaction times, and both groups had slower reaction times in the distress condition compared to the easy condition. Okay, so the PACE-AT recruits multiple functional domains, such as sustained attention, information processing, working memory, psychomotor coordination, and speed, and cognitive strategy, and whatever part of your brain does math. And so it's not surprising that it elicits activation in this cognitive control network, and it deactivates the default mode network, and this is during that mental math test. And of course, there's also that feedback, and some of that feedback is very unexpected. In the easy phase, there's kind of the oops contrast when they don't hear anything because they were incorrect, which happens maybe 20 to 25% of trials, versus when they were correct and on time, I heard that bing. You can see this widespread activation, especially in the anterior insula, inferior frontal gyrus. It's part of the salience network that alerts you to something that unexpected happened. And then there's the oblique condition where you hear the buzzer even though you know you're correct and on time, compared to when you hear silence because you're correct. This buzzer condition happened on maybe 65% of trials, so it's much more frequent. And so the only real difference between these two conditions is that the height of activation was much stronger for the easy phase, possibly just because the events were more rare. So that's one way of analyzing this data, but the way I prefer to look at the data is using task-based functional connectivity, in particular using generalized psychophysiological interaction models. So traditional BOLD can show co-activation of different regions, but these GPPI models can perhaps show communication between regions. It does that by measuring dynamic changes in functional connectivity within an experimental task. So on the top line, this represents that the task came on, they're doing the mental math, and then they're resting, and the task comes on, and so forth. And for this analysis, you need to identify a seed region of interest. In this case, I was interested in the bilateral auditory cortex, because that's what's registering the beeps and the buzzers. And this analysis takes the average BOLD signal from those seed regions, looks at it across time, and then takes the average or the BOLD signal from every other voxel in the brain and looks at that across time. And this equation down here looks at the interaction with the task and kind of tells you what parts of the brain were more strongly correlated during the task than at rest. And the results are a little bit open to interpretation. I think if there's a strong positive correlation between two regions, it shows engagement or communication, that they're both working on the same problem. If there's a negative correlation between two regions, it might be an inhibition or a disengagement. And if you just look at the contrast of where in the brain was there stronger positive connectivity in the distress phase compared to the easy phase, you see a number of different regions that are significantly different. But I think what's a little bit more informative to actually extract connectivity values. So for each cluster up here that was significant, I extracted the values and I graphed them. And I found that there were a number of regions that all had the same pattern of contrasts. So this graph is just made up data. It's just showing you the different patterns that I found in the different brain regions. So for instance, the middle, superior, and inferior frontal gyrus and anterior insula, as well as in the posterior parietal areas, which is part of the cognitive control network up here and anterior insula over here. All these regions had the same pattern. When they heard the tone during the easy task, there was a strong negative connectivity with the cognitive control areas. And the opposite was true when they heard the buzzer. The buzzer actually seemed to engage those regions. An exact opposite pattern was found in the ventromedial prefrontal cortex, which is up here. This region is involved in reward processing, and you tend to see greater BOLD activation with this larger reward value. So I think that's consistent with my results here. That ping that tells you you're correct and on time, engage that region. And that's maybe why you find it rewarding. But the buzzer disengaged that region. And then there were parts of the middle and superior temporal gyrus over here that were positively connected, whether they heard the ping or the buzzer, but it was much more strong during the buzzer. I think these are additional auditory processing regions. The buzzer, it's unexpected. It takes you a little bit more time to process and take more brain regions to process. And lastly, this pattern was found in the mid-insula, central operculum, putamen, which you see over here, and the pre and post central gyrus, kind of up here. And these are all motor and sensory areas. So perhaps when you hear that feedback, there's some motor inhibition going on because you're waiting for the feedback before you make your next selection. But it looks like if this is inhibitory, that the buzzer sound was much more inhibitory than the tone. So this makes sense to me because I've played this task dozens of times trying to fix bugs in my code. when you hear that bing in the easy test and it's super predictable and it's just telling you something you already know, it's really easy to ignore it. I mean, it's a nice little ping you get, and then you stay focused on the task. But when you hear that buzzer and it's unexpected and it's giving you bad news, you can't help but think, oh, did I add them up wrong? Did I select the wrong response? And by the time you've processed what just happened, a couple more numbers have flashed and you don't know what you're doing. So it's very distracting. It makes sense to me that that buzzer actually engages the cognitive control regions and detracts from your ability to stay focused on the task. Okay, so back to my smoker, ex-smoker differences. I didn't find any main affective group, but I did find a group by condition interaction effect. There were similar patterns of positive and negative connectivity, but the smokers' differences between conditions was larger. And it happened in the lingual gyrus, in a couple places, in the anterior insula, and in the inferior frontal gyrus. And the anterior insula IFG regions are activated in studies on visual and auditory attention. They help detect salient events, and they're involved in inhibitory control. And the lingual gyrus back here in the occipital cortex may be involved in visual attention and is active in attention tasks. So looping back around to the negative mood and how that could have affected cognitive performance. I looked at the correlation between those two things separated by group. And I found another group by condition interaction effect. Among the smokers, but not the ex-smokers, there was this negative correlation. So the negative mood slope means I converted those 3 time points into a regression slope. So larger value here means they were reporting more negative mood across those 3 time points. And this is the overall percent correct. So the smokers over here reporting the greatest increases in negative mood, and they're performing the worst. And it makes sense to me that if you're getting more incorrect, you'd be more stressed out. And I'm surprised that's only happening in the smokers. So another hypothesis for the stress-smoking relationship might be that smokers actually struggle just a little bit more with cognitive decision-making, and that can actually elicit a negative mood. On the flip side, maybe they're more sensitive to the negative feedback and the negative emotions it elicits, and that interrupts their concentration even more. So in light of that correlation, when I started looking at cognitive performance by group and negative mood by group, I controlled for the opposite one. So I looked at interaction between the PACET connectivity and cognitive performance by a group controlling for negative mood. And what I found was in these regions that kind of overlapped with the main interaction effect, the anterior insula and inferior frontal gyrus. Among the smokers, but not the ex-smokers, the most accurate smokers up here had the largest differences in connectivity to stress greater than easy. And the relationship between the functional connectivity difference and the percent correct was stronger in the smokers than in the ex-smokers. So as a nice sanity check for maybe what's going on, this paper came out kind of recently in 2022. They did a meta-analysis of a bunch of different studies that studied interoception, which is your awareness of the physical and emotional state of your body, as well as decision-making tasks and emotional regulation tasks, which is like telling yourself to calm down when you're angry. And they found that in every case, there was significant overlap in the anterior insula, and conveniently in the right anterior insula where I found my results. So we've known for a while that the insula is involved in interoceptive awareness and processing salient events. I think this gets us a little step closer towards understanding what exactly it's doing. But I think maybe the insula and IFG might be acting as like a fulcrum between attending to bottom-up sensory awareness of stimuli and how it's making you feel, and a top-down attentional control. So it's like you can attend to that buzzer, or you can stay focused on the task and do the math. You can't do both. And the insula is kind of deciding which one you're going to attend to or ignore. Okay, so I'm going to kind of swerve to the left and discuss some other data analyses that I did on this data set. To complement that hypothesis-driven region of interest analysis that I used in the GPPI, I also did this data-driven multimodal fusion analysis with my collaborator, Dr. Jing Sui. So she's the mathematician, I'm not, but I think what's going on is this is combining three complementary imaging modalities that we tend to always get in the scanner, getting the gray matter volume from the structural image. We're getting the fractional anisotropy, which is a measure of white matter integrity from the diffusion image. And we're also getting a measure of the fractional amplitude of low frequency fluctuations from the resting state functional MRI. So I think our study recently showed that regional differences in FELF actually correlated with glucose utilization in these different regions in a PET scan. So I think it's maybe a measure of brain metabolism. But anyway, this analysis converts all the data into a matrix where each column represents a voxel and each row is a subject. And then it looks for independent components that all kind of hang together and correlate together. And then you introduce a variable of interest. In this case, we introduced variables that were already significantly different between the two groups. And we can look at what correlates with them across subjects. So on the top row is the PACET percent correct, or PACET accuracy. Then it asks, did any of the independent components that were initially investigated or discovered correlate with that variable of interest? And we found that it did. So these are the regions that were different between the smokers and ex-smokers and correlated with PACET performance accuracy. And the interpretation of this data is kind of speculative. This is a much smaller sample size than we usually have for this kind of data. But the one thing that really stood out to me was that there were differences in FELF, again, maybe the metabolism of the brain. Smokers had more FELF than ex-smokers in the parahippocampus going into the hippocampus. And ex-smokers actually had more gray matter volume than smokers in the parahippocampus, extended hippocampus. And those regions are really important for like short-term working memory. And the PACET really relies on those things. So maybe this reduced gray matter volume, but maybe a compensatory increase in metabolism, it appears to be related to the worst performance among the smokers. And again, nicotine is a mild psychostimulant. It tends to improve reaction time and performance in non-smokers, but it's all those toxins in cigarette smoke that build up in the brain that cause inflammation in particular. And that's thought to be why smokers tend to have differences in gray matter volume and white matter integrity. So moving on to DNA methylation. So a grant reviewer had asked me to collect DNA samples for future testing. So I had all these saliva samples at the end of the study and I didn't know what to do with them. And I asked a collaborator, what should I do? And she said, you should test it for methylation. I said, great, what's that? And she explained that this is an epigenetic signaling tool that regulates gene activation and expression. And cigarette smoking is associated with extensive genome-wide differences in DNA methylation. In particular, it's associated with the hypomethylation of this CpG site on the aryl hydrocarbon receptor repressor gene. This gene regulates the aryl hydrocarbon receptor, which is the induction point for the xenobiotic pathway responsible for the degradation of environmental toxins commonly found in cigarettes. And this hypomethylation is probably due to the polycyclic aromatic hydrocarbons found in cigarette smoke. These are byproducts of combustion that are found in all smoke. The cigarette smokers get a lot of smoke in there. So the literature has really quickly identified this CPG site as being a biomarker for smoking status. This is one of the most reproducible CPG effects. And so in our sample, even though we had like a small sample and you were using a saliva sample, we found that there were two CPG sites in particular that really stood out and were significantly different between our two groups after correcting for multiple comparisons. There's the AHRR, which is the one we talked about just before, and the ALPPL2. And there was a bunch of other CPG sites that were significantly different at P of 0.001. But it was mainly those two that were different. And this just shows the ROC curve, which validates a lot of previous, these are results in the light of a lot of previous studies that there was very good specificity and sensitivity among our sample to identify smoking status based on this AHRR. Smokers are hypomethylated, meaning that we think there's more gene activity going on in them. And what got me really excited about using this AHRR marker as a biomarker of smoking status is that when we pooled everybody together and correlated it with longest abstinence duration, that includes the smokers and the ex-smokers, there was a really strong correlation. And there was also kind of a modest negative correlation with pack years, and that's including the ex-smokers. So it's exciting because it's better than self-report. Any physical biomarker is better than self-report. And two, it's counting for variability both in how long they've abstained, as well as how heavy they were smoking and how long they smoked back in the day. So it's potentially accounting for more variability than just one variable or the other. There's no relationship with nicotine-dependent severity, but there was a positive correlation with pace-% accuracy. So ex-smokers performed a little better, and they had more methylation on this CPG site. And I think this is one of the best evidence that suggests that ex-smokers are actually showing improvement in cognitive performance after quitting as a function of their abstinence duration. It's not just simply a problem of like having a cross-sectional study. So while I'm focusing a lot on that AHRR, I just want to show you that across all the CPG sites, they were significantly different. Some were hypomethylated and some were hypermethylated in smokers compared to ex-smokers. And there's been a number of different studies, and not all of these CPG sites replicate from study sample to study sample. Sometimes it's influenced by the sample's demographics. And then lastly, my collaborator, Dr. Shi at UMS, ran this data through a software called Ingenuity Pathway Analysis. And this software is linked to PubMed and everything in PubMed that connects CPG sites and genes to disease states and health conditions. So it fills in some of the gaps of the identified CPG sites, and it connects it to CPG sites that tend to hang together in the same network. And then it runs an analysis of like the top health conditions that are implicated in this network. So unsurprisingly, the top network affected was cancer, organismal injury, abnormalities, and cardiovascular disease. So that's unsurprising, but yet it's a small sample. These were saliva samples, and we found the most reproducible thing out there is that smoking causes cancer, and ex-smokers have a reduced risk of cancer. It's great. So back to that supervised fusion analysis, I ran that AHRR percent methylation as the supervised part of this, looking for if there's any components that correlate with that, as well as the abstinence duration. And both of the networks that correlated with those two regressors had overlapping patterns in several brain regions, but the methylation network encompassed a lot more regions, which I think that makes sense if you think it's accounting for more variability than just abstinence duration alone. And I don't want to overinterpret the data, and I'm still analyzing these results, but I just want to point out there's something going on in the anterior insula and inferior frontal gyrus. In this case, it looks like the smokers actually had more gray matter volume in a way that was related to the hypomethylation of the HRR. And so I'm not trying to suggest that there's a causal relationship, that biomarker are just indicative of the heaviness and duration of their smoking, their abstinence duration, and maybe how much their body has recovered from the effects of smoking. But there was a recent study that did a post-mortem analysis of several different brain regions, and they did find that some brain regions had hypomethylation of this AHRR. So potentially in the future, we could discover that there's kind of a direct link between this AHRR hypomethylation and changes in the brain. Okay, and just some limitations. Of course, this was cross-sectional instead of longitudinal. I'm getting a lot of flack from the reviewers about that. But my ex-smokers were at 9 years quit. Try to design a longitudinal study where you bring in enough smokers that in 10 years, you're gonna have a decent sample of ex-smokers. I mean, there's some really, really big ongoing longitudinal studies that do that, but it's logistically insurmountable for like one little investigator to do. And I think the addition of that AHRR biomarker makes a really strong argument that the differences that we see along this correlation are due to changes in smoking status. Of course, I didn't get saliva samples from everyone, so my sample size was even smaller than it might have represented. We didn't even get quality scan data from everyone that provided a sample, so I'm excited to do similar things in the future with larger sample sizes, of course. But I've already leveraged this R21 data into an R01 project. The next step is I'm gonna kind of do the same thing and bring everybody in. They're undergoing that MRI scan with the PACEAT and looking at individual differences in their stress sensitivity. And then they make a quit attempt. And we track them using ecological momentary assessment during this quit attempt to look at the relationship between negative mood, daily hassles and daily stressors, and their smoking occasions. And lastly, I'm really interested in using that AHRR biomarker to investigate the recovery of brain health in smokers who quit completely compared to smokers who switch to e-cigs. That AHRR CPG site will not be affected by e-cig use because there's no combustion in e-cigs. But you would expect there to be maybe a linear relationship between smokers, ex-smokers, and non-smokers, and maybe ex-smokers who are using e-cigs look more like smokers than they do non-smokers. And also furthermore, there's a lot of preclinical research that suggests nicotine itself is causing inflammation in the brain. And it might be the nicotine itself that sensitizes people to stress. So from like a neck down perspective, if you are smoking cigarettes, you should probably switch to e-cigs. It's probably healthier for everything else in your system, but for as far as brain health is concerned, we don't know yet. Okay, so I'd like to thank my collaborators, Stacy Daughters, and Jing Sui, and Shilei Chi, and Ping-Ching Shi, and NIDA, and a court grant from UAMS. Thank you so much, and ask me any questions.
Thank you very much. That was great. Is there anything else?
Not yet.
Okay, I had a question. In terms of the smokers versus ex-smokers and their reaction to stressful stimuli, or the failure experience, I guess. So there are endogenous systems by which we can control our emotional reactivity. Do you think if somebody's an active smoker, they're taking these internal loops kind of atrophy because they have an external loop? If they feel something stressful, they'll light up and then that'll quench it. So how can we kind of train the internal systems to be a bit stronger and kind of make it not so likely that we relapse into stressful circumstances?
Yeah, I know there's been some research on distress tolerance training for smoking cessation. It hasn't really, I mean, it's been incorporated to a lot of different therapies, that emotional regulation component. They do like feedback MRI research where you can see actual changes in activation in different brain regions and then train yourself to reduce the activation. I would love to see some therapy where you're shown that internal validity that like doing this therapy actually reduces or strengthens. In my case, you'd need to strengthen the connectivity with the insula when there's negative feedback. So that'd be a cool step.
I know there's a lot of expertise about adolescence here. I think in terms of how adolescents kind of develop the ability to kind of, soothe themselves. And that's kind of impaired with taking up smoking in adolescence. Other questions?
So I was thinking, I remember thinking about like other stress during gestation and I guess hindering people development and the cortisols and stress reactivity in children. Is there any evidence that I guess mothers or brothers carrying stress is associated against the vulnerability to eventually smoke with them?
There's another stress response effect, the enhanced stress response. They absolutely without the literature. Yeah. So epigenetics suggests that sometimes when there is a change in methylation, in some instances,
It is. Yeah.
especially stress related.
Yeah. A lot of the imprinted genes have to do with brain function. So in terms of the changes with e-cigarettes versus the conventional cigarettes, because you lit up, so to speak, this AH receptor mechanism that's induced by the combustion products that aren't present in the e-cigarettes. So would you think that some of these other changes in stress response and other kind of imaging changes you see would be absent in the e-cigarette users?
So no, so there's that research suggesting it's nicotine itself
Yeah.
that's interacting with the acetylcholine modulation of the stress response.
I see.
And so it's potentially people who are using e-cigs would have the same stress vaping relationship that you would find in smokers. But the vaping does not affect that. There's ongoing studies looking for other methylation markers of e-cig use. But I don't think any one thing has come out as a biomarker yet.
Neuroscientist, but if I read it correctly, the brain sort of recovers as well. So is that true for other substances? Just alcohol?
There's a foreign CBG site that actually is a better biomarker for lifetime alcoholics than any supplement. They're so bad at supplements. So that's there's the abstinence from alcohol that is the same. They're 25 to 55.
Question just is, you may have said this, but how did you handle just the state sniffers? I don't know how long the testing procedure was, but it's always a question of like, what's the sort of baseline state sniffers in terms of, right before the procedures and depending on how long the session went on, if there was stressful affected by withdrawals in terms of merging or post that time.
abstinence. So these were some associated with I also asked if they were craving across the time, and yeah, that was right up the wall. And that could be just a time effect too, and have he controlled. But doing medicine, unfortunately, it's not to do that exact thing. We're going to overnight abstinence versus satiated. And they would have reduced the stress levels when they're abstinent.
You've been looking at, I don't know if you could look at, like, the data that you have, like, look at correlation and their performance and stress tolerance or something like that. Maybe that you have a ceiling effect and they're all craving so much by that point that you can't really look at correlation. So, yeah.
In terms of the patch, maybe I missed the difference. Is there literature to show that the patch decreases stress for people trying to quit smoking?
I imagine it reduces stress and it reduces withdrawal.
I think,
All symptoms are stressful.
yeah, I just wondering your paradigm for that. It might kind of make a smoker look like a smoker because they're not going through a withdrawal.
Usually don't really patch all that long. I mean, I don't know how long you have to be absent from smoking to start seeing a change, no matter what kind of structure.
Oh, I
I imagine that would be a stress response. Someone less.
So,
Chat.
Oh, no. Those are mostly just me letting people to notice and questions.
oh, I see. Okay.
Sorry. Someone say that they really love the talk.
Oh, that's good. Well, I want to thank you for a great talk and appreciate you coming by.